right, let's put this all together. The last gas law, our ideal gas law. So since we know that pressure, temperature, volume, and the number of moles of a gas all are proportional or inversely proportional to each other, we can solve for any unknown one of those variables. And we can solve for it if we know something called the universal gas constant. And it has the symbol of R, and it has the symbol of R because U is used for uranium. Ta-da, done. So I'm going to flip screens for a moment, and I'm going to derive R for you. Let's get a value for R when the pressure is in kPa's. IB only uses the R value when pressure is in kPa's. So I'm going to take half of the combined gas law. So that's P1 V1 over T1. And I'm actually going to add something to this here. I'm going to add the number of moles in the denominator because volume divided by the number of moles, well, that's just Avogadro's law. So we really have all 5 formulas represented in just that little expression. And then what I'm going to do, I'm going to set that all equal to our universal gas constant. Then I am going to remember from previous videos that at STP, pressure is 100 kPa. I'm going to remember that 1 mole of the gas at STP will take up 22.7 liters worth of space. I'm going to remember this is all for 1 mole, and that at STP, my temperature is 273 kelvins. And yes, for the ideal gas law, your temperature has to be in kelvins. So let's just shove it all in. I've got a pressure of 100. I've got a volume of 22.7. I've got 1 mole. And I'm going to consider these all lit values, by the way. And my temperature is 273. And when I solve this all out, and I want to do it to 3 sig figs, because that's what IB recommends, I get 8.31. And my units are going to be just reading off the units for each one of the variables in my expression. kPa liters divided by mole temperature, kelvins. This is your universal gas constant. I would definitely write that down and make a note of that before we get the ideal gas law. All right, so now let's get my ideal gas law, your ideal gas law. I'm going to rewrite that half of the combined gas law in terms of the universal gas constant. And this is all scientists decided to do to get the ideal gas law. They decided to move the moles times the temperature over to the right-hand side by multiplying by the reciprocal. And you get this final expression of PV equals NRT. And you know why they put the N out in front of the R? Not that it matters in terms of order of operations, is because it sounds kind of interesting and easy to remember that the ideal gas law sounds like PIV-NERT. PIV-NERT. So you can put your own spin on that one. There's your ideal gas law. It'll be formalized for you in a second. So here it is, the ideal gas law. PV equals nRT, pressure times the volume of a system will equal the number of moles of gas in that system times the universal gas constant times temperature in kelvins. Please do not forget to change that temperature to kelvins. Also remember that IB, we're only using the pressure when it's in kPa's. So you'll see some practice problems where it's in ATMs, and I might give you the R value for that, but IB will only use the pressure in kPa's. So please take a moment. This needs to be written down somewhere, highlighted. This is your formula. that you're going to use in the next practice problem. So here's our little bit of practice. I put a little twist on this because a lot of times you're not given moles, a lot of times you're giving mass instead. And so it's combining two formulas together, which is great practice for IB. It says a 0.230 gram sample of a gas had a volume of 0.0785 cubic decimeters at 95 degrees Celsius and 102 kPa. Determine the molecular mass of the gas. So, I got two things going on here. First thing I have going on is that in PivNert, my PivNert equation, it contains nothing with mass. So I'm going to substitute this formula here in for, I'm going to substitute this formula in for the number of moles. I'm going to call this formula here to find the moles, the little m for mass divided by the big M for molecular mass. Molecular mass is just that value you'd get off the periodic table when you add the masses of the elements together. So I'm going to rewrite this now as PV equals little m over big M times the universal gas constant times temperature. The goal is to find the molecular mass, big capital M. So I'm going to multiply both sides by big capital M. And that's going to move M from the right side to the left and putting it in the numerator. And then what I'm going to do is I'm going to divide both sides by pressure and volume. And that's going to move the pressure and the volume to the right-hand side, leaving me with an expression to find molecular mass. Molecular mass is going to be my mass that I'm given, universal gas constant, times the temperature, all divided by the pressure times the volume. And here I am already to fill stuff in. I've isolated my molecular mass. So my mass here is going to be 0.230, 3 sig figs there. Universal gas constant 8.31. Temperature, oh, I've got to change that Celsius to Kelvin. So I've got to say 273 plus 95. So this is going to give me 368. Don't forget to change your temperature to kelvins. All divided by a pressure of 102 times a volume of 0.0785. And we're ready to solve. So I'm going to say 0.230 times 8.31 times my 368. Get that answer and make that answer 3 sig figs. So I multiply the numerator values together to get 3 sig figs. So I get 703. I'm going to have 3 sig figs on the denominator as well. 102 times 0.0785. And I get 8.01. I'm going to solve this problem right before the train comes. Yay! So 703 divided by 8.01. 703 divided by 8.01 gets me a molecular mass of 87.8 grams. And this is going to be actually grams per mole because it's a molecular mass that I added up from the periodic table. So hopefully this combined together a reminder of stoichiometry, how to get the molecular mass. Combine that with the ideal gas law. Again, you're going to see more practice after this, and we will have definite review sessions during our class and office hours. See you soon.